Welcome. So now we look into how to use GAMS to solve the mixed integer linear programming problem formulation which we had developed for production planning problem. So if you remember the production planning problem, we had this data of selling price and the capacity L, M and H. We had the production cost corresponding to this capacity levels CL, CM and CH. Similarly for investment cost we had IL, IM, IH, and for raw material we have three types of raw material, right, raw material 1, raw material 2 and raw material 3. Here we have shown you only 18 process, but if you remember there were 54 processes which can be used to produce 24 products, right. For the case study which we had taken, there was no limit on raw material 3, right. So it was assumed that raw material 3 is available in abundant, right. So there is no point of including a constraint on raw material 3. So we will only use raw material 1 and raw material 2. So first we need to code this data into GAMS, right. Once we have got the data, we will then subsequently include the model equations, right. So what we are doing here is we are defining three sets, process 1, process 2, process 3 or the name of the process, or we can just have numeric values, right. So what we are doing is we are writing 1 star 54, right. So this is equivalent to writing 1 comma 2 comma 3 comma 4 all the way up to 54, right. So compactly it can be written as 1 star 54 within those slash. So remember whatever we give within slash corresponds to the value of that particular set, right. So now set J has 54 elements 1, 2, 3, 4, 5, 6 all the way up to 54. The set LEV has 3 elements L, M and H, right. The set K, right, has 2 elements R1 and R2. Now we have defined a set for the processes, the levels and the type of raw material, right. So first let us get the detail of the raw material. So we define a table, right. We define a variable Rm, right. So Rm runs on the set K comma J. So K comma J means K is for the raw materials and J is for the process, right. So it will be 2 rows because we have R1 and R2, and it will have 54 columns from 1, 2, 3, 4, 5, 6, 7, 8 all the way up to 54, right. So here we have R1, R2 because we have used R1 and R2 over here. The values are R1 and R2. So we write the same values R1, R2 over here, and over here we write the process number 1, 2, 3, 4, 5, 6 all the way up to 54. That is how we have defined our set J to indicate the process, right. So we get this value 0.948. So that is process 1 raw material 1. Process 2 raw material 1 is 0.9432. Similarly we enter this entire column over here, right. Here we have shown you only 8 values, but all the 54 are to be entered. Similarly we enter the values for the second raw material. So for the second raw material, the first 18 processes do not use it, right. So that is why you see zeros over here. So if you go back and look at the data which we have given you, the subsequent processes do utilize raw material 2, right. So those values would be entered appropriately. Then we want to enter these values, right, the capacity values. So we define a table, right, with a variable name C, right, to denote capacity, and it is going to have 3 rows and 54 columns. 3 rows because we have 3 elements in the set LEV. This corresponds to this levels, 3 levels and 54 process, right. So over here the set used for indicating the levels L, M, H are LEV. So we write LEV over here, and the set used for denoting the process are in the set J. So we have J over here, right. So and then we enter the values, right. So L, M, H are the values of the set LEV, right. So L, M, H, and those are in the rows. So for example, level 1 process 1 is 70. So process 1 indicated by this one, level L is 70. Level M it is 135. So for M process 1 it is 135. For process 1 H is 270. So we write 270 over here, right. So what we see over here as column vectors have become row vectors. So similarly we define 2 additional tables PC and IC. Their structure is similar to this capacity, right, LEV comma J, and we appropriately enter the production cost for the 3 levels and the investment cost for the 3 levels, right. So we have got this data, we have got this data, we have got this data, we have got these 2 raw materials. Raw material 3 we are not including because there is no constraint on it. Now the only thing that we need to include is the selling price. So here if you remember, the selling price of product T1, no matter from which process it is produced, it is 0.975, right. So, that is what we are doing now. We are defining a parameter SP, the name of the parameter is SP, it runs over the set J, right, and J indicates the process. So, J contains the values of 1, 2, 3 all the way up to 54. So, we have 1, 2, 3, 4, 5, 6 all the way up to 54, and then we enter the corresponding values of selling price. We have one more parameter on the amount of raw materials which are available. So, we have two types of raw materials. So, we define a parameter R, right, it runs over the set K, right, and set K contains these two values R1, R2. So, the value of raw material 1 that is available is 500 and the value of raw material 2 that is available is also 500, right. So, all these which you see over here are description of the appropriate variable. We also define a scalar B to denote the budget, right, and the amount of budget that is initially available is 1000. So, we supply that using the syntax of GAMS. So, just to quickly run you through what we have done so far is we declared 3 sets and we assigned values to them. Then we created a table to provide the amount of raw material which is required in each process. We have another table which gives the production capacity for each production level, and then we gave the production cost and the investment cost corresponding to each process and the appropriate level, and we have this vector SP which denotes the selling price of the product, and we have another vector over here which has the amount of raw materials which are available. Finally, we have this scalar which shows the amount of budget that is available, right. So, as of now what we have done is we have included only the data into the GAMS model file, right. Again, remember, here we are showing you only a cropped version. All of this runs all the way up to the 54 processes which we have. Now, let us define the variables which we have. So, this is the mathematical formulation which we had developed, right. So, here if we see, we have 6 types of variable yj, zj, xj, lj, mj and hj, right. So, that is what we are defining, variables with the keyword variables x of j, y of j, z of j, l of j, m of j and h of j, right, and it runs across the set j, and we know that the set j we have defined it as 1 star 54. Since we have defined the set j to have the values 1 to 54, defining the variables over here means x of 1, x of 2 all the way up to x of 54. Similarly, y of 1, y of 2 all the way up to y of 54. So, this holds true for all these 6 variables, right. And if you recollect our previous discussion, we need to define a variable for the objective function, right. So, in this case what we are doing is we are defining the variable to be obj. We will use the variable obj to determine the objective function value, right. So, among these variables which we have over here, right, lj, mj, hj are positive variables, right. Once we say lj, mj, hj are positive variables, in view of this equation, right, xj will also be positive, or we can even give comma x of j over here and then a semicolon wherein we define all the positive variables. Yj and zj are binary variables which we have, right. So, we have this keyword binary variables and have y of j comma z of j and then end it with a semicolon. So, in this block we have defined all the variables and their types, right. Now, we need to define the equations. So, what we will do over here is we will take the same equation numbers which are given over here. So, this equation we will call it as EQN1, EQN2, EQN2 and all the way up to equation 7, right. And all of this equation, if you remember, it is to be written for all the processes, right, 1, 2 all the way up to j. So, this is true for equation 3, equation 4 and equation 5, whereas this will be only a single constraint because there is only one investment cost, right. Similarly, this equation will come twice, right, or k times. In this case we have 2 raw materials, and the objective function we define it with the equation name profit. So, the name of this equation is profit, the variable is obj, right. So, the name of the equation which we will use for coding the objective function is profit, and then we have all the equations, right. So, equation 1 is this one which runs across j, equation 2, 3, 4, 5 run across j, right. So, this is equation 2, 3, 4, and phi. So, these equations run across the set J. Equation 6 is a single equation, right. So, we do not write equation 6 within brackets anything, right. Equation 7 is for the k types of raw material. So, over here we have defined the set k to contain 2 values, right. So, when we write equation 7 of k, it basically means we will have 2 equation 7 of R1 and equation 7 of R2, because this set k contains values R1 and R2. So, now that we have defined the data which is required, we have defined the variables and their types, we have defined the equations which we are going to use. Now, we need to define the equations themselves, right. So, over here we say name of the equation profit dot dot and then obj equal to E, right, because the objective function is now written as an equality constraint. So, the value of the objective function is carried over to obj. Over here if we see this particular equation, right, it is summation of Sp and Xj, right. So, summation of the variable Sp and X, right, over the set J, right. So, that is why we write sum over J, right, the variable Sp and the variable X. So, that is this particular term over here, right. Then we have this second term which we need to write. So, for that what we would do is sum, we need to sum over the index j, right. So, sum over the index j, CL is indicated by PC over here, right. So, PC of L, right. So, PC of the set L comma j for the jth process multiplied by L of j plus PC of M, right, comma j into M of j plus PC of H comma j into H of j, right. So, that is what we have written over here. So, over here if we see whatever we have written in the typical mathematical form over here can be directly coded in GAMS. So, again here we have used PC of L comma j and not PC of LEV comma j. So, PC of lev comma j if we write, it will access all the 3 elements, which is not what we want over here. We only want the production cost corresponding to the low level, right, and the set LEV contains the values L, M and H. If we want to access a particular element from that, we can directly write that element within single quotes. That is how we have written the second part of the objective function. So, then equation 1, right, is L of j is less than equal to y of j, which is straightforward over here, right. Equal to L equal to is for less than equal to constraint. Similarly, equation 2 is H of j is less than or equal to 1 minus y of j. Equation 3 of j, right, is L of j plus M of j plus H of j is equal to E equal to, right. So, equation 4 is over here, right. So, here again similar to this CLJ we need to access LJ, right. So, what we are doing is x of j is equal to E equal to. So, if you remember L, M and H we have saved in the table C and we have used L, M, H over here, right. So, what we do is C of L within single quotes comma j star L of j plus C of M comma j plus M of j, and similarly we write for the last term also, right. So, this equation is similar to how we constructed the second part of the objective function. Equation 5 again is straightforward. So, equation 6 over here is similar to how we wrote the second part of production cost. So, this is similar to this part over here, except that instead of PC which denotes production cost, we have defined the investment cost as IC, right. So, if you compare this second part of this profit equation and this equation 6, you will see that it is similar. So, this is the investment cost which will be required for whatever we decide to produce, and the amount that is available is B, right. So, this B we have defined it as a scalar initially. So, this should be less than equal to the budget, right. So, similarly the 7th constraint over here, right. So now this constraint is not to be written over J, it is to be written for all types of raw material, right. Over here also we had defined equation 7 of K. So here we have equation 7 of K, and then over here we have summing over the jth raw material. So sum J comma Rm, which is the name of the table of K comma J. So if you look into this table, right, so this K was the type of raw material. So that was in the row and the processes are in the column, right. So that is why we write Rm of K comma J multiplied by X of J. So that has to be equal to capital R of K, right. So capital R is a parameter which will contain two values because it runs over the set K, right. The set K has values of R1 and R2. So now we have coded all the equations which we have developed in GAMS. Now we need to construct the model. So we use the keyword model, right, and name of the model that we are giving is petrochemical, right, and we want to include all the constraints which we have written over here. So within two slashes we write the word ALL and end it with a semicolon. So this line over here will help us to construct the model. Once we have constructed the model, in this case we know it is a mixed integer linear programming. So in GAMS, as we discussed earlier, mixed integer linear programming is denoted by MIP, right. So here we have solve the name of the model petrochemical using the default solver of mixed integer programming while maximizing the variable obj. So when we maximize the variable obj, we are basically maximizing this expression over here, which is nothing but the profit, right. So we also want GAMS to display the final values of the decision variable X, the decision variable L, the decision variable M and the decision variable H. It will give all the values, but in the display part we want to display these particular 4 variables. So each of this variable will have 54 values because X, L, M and H, each of them run over the set J and the set J contains 54 values, right. So here it will display 54 into 4 values L, M, H and X. So now that we have constructed the GAMS model, we can execute it, right. When we execute the GAMS model, we will get two files, one is the list file and the log file. You can browse through the list file, right. So over here we will just discuss the values of the decision variables. So this is a section of the list file. So right now we have shown only the variable X, right. So for variable X, if we see, the lower bound is given, the upper bound is given. We did not explicitly specify X to be a positive variable, right. So that is why it is showing the lower bound to be minus infinity and the upper bound is plus infinity, right. So since we have 54 processes, right. So if you remember, X was running over the set J and the set J had values of 1, 2, 3 all the way up to 54, right. So that is why we have 54 over here. Out of the 54 processes, only process 3, process 4, process 46, process 47, process 48 produce a particular product, whereas the other 49 process do not produce anything. If you execute this program and also look into the L values, M values, H values, you will be able to observe these values. Similarly, you can also look at the Y and Z values, right. So for P3, P4, P46, P47, P48, the amount produced is given as over here and the L values are 0 for all of them. So for all this process, the production is either at M or at H or in between M and H, right. So for example, for process 3, if we see, even the M value is 0 and the H value is 1, right. Remember, this H is the uppercase H, not the lowercase h. The lowercase H value for process 3 would be 310, right. So that is why when it produces 310 from process 3, the capital H takes the value of 1. Similarly, for process 48, the amount of production is at the high level. For process 47, the amount of production is at the medium level corresponding to the value M, right. For the rest of the two processes, P4 and P46, it is somewhere in between M and H. Since all these processes are used, the value of Z would be 1, which is as expected, and the value of Y would be 0 because the production is between M and H. So this is the production plan that we obtain using GAMS, right. So the profit for this production plan is 712.5. So here if you see, we have something called as absolute gap and relative gap, right. So here absolute gap is 51.875527 and relative gap is 0.067866. So we have got this profit of 712.5040, but here if we see, the absolute gap shows a very large number, and over here we also get this statement, solution satisfies tolerance, right, and that is why the solver terminated, right. So first let us understand what is this absolute gap and relative gap, and then we will come back to this model. So we need to understand two terminologies over here, one is absolute gap and one is relative gap, right. So to understand absolute gap, we need to know what is best integer and best estimate, right. Since we have already looked into mixed integer linear programming, you would be able to understand that best integer is integer solution which has been obtained so far, right. So far in the sense as far as the branches have been explored. So let us say while exploring some node, let us say the best integer is 10 and the best estimate is a bound for the optimal integer solution. So let us say 15. So this discussion is for a maximization problem. So absolute gap is the absolute distance between best estimate and best integer, right. So over here the absolute gap is 15 minus 10, which is 5. So when we are exploring the search space, this absolute gap can be calculated, right. So the default value of the parameter opt_ca is set as 0. If our absolute gap is less than opt_ca, so this is a user defined parameter, right, the default value is 0. So if we get an absolute gap which is less than or equal to opt_ca, then the algorithm terminates. In this case our opt_ca is 0, the default value. So the absolute gap which we had was 51.87, right. So this condition is not satisfied, yet the algorithm terminated, right. So in addition to this opt_ca, we also have one more option known as opt_cr, right. To understand this opt_cr, we need to understand relative gap, right. So relative gap is given by this formula, right, the absolute gap, which in this case is 5 because that is what we have calculated, divided by max of absolute of best estimate comma absolute of best integer. So best integer in the current case is 10, right, and best estimate is 15, right. So max of absolute of 15 comma 10, so that is 15, right. So this value comes out to be 15, so this is 1 by 3. So this is how we calculate relative gap, right. So the default value of opt_cr is 0.1. So similar to absolute gap, during the search procedure we can also calculate the relative gap, right, and if this relative gap which we calculate is less than or equal to opt_cr, which is the default value is 0.1, right, then the algorithm would terminate. So in the current case we had a relative gap of 0.068, right. So since this condition is being satisfied, the algorithm terminated despite the fact that the absolute gap is a very large value. So this calculation of opt_cr varies from solver to solver, right. In Simplex it is not calculated using this formula, but it is calculated using this formula. So all these details are available in the solver manual as well as GAMS manual, right. So over here it is absolute gap divided by 10 power minus 10, a very small number, plus absolute of the best integer solution. So in this case it works out to be 0.5. So depending upon the solver with which we are working, the relative gap would be calculated using this formula or this formula, right. So in any case, if this condition is satisfied, that whatever value of opt_cr is set, if it is greater than or equal to relative gap, right, as and when we achieve a relative gap which is less than or equal to the opt_cr, the algorithm terminates, right. So in this case, since this value was 0.1 and this value was 0.068, it terminated, right. So the reason for termination is this opt_cr, right. So we can decrease the value of opt_cr. So this is the same code which we have discussed previously, except for this line in which we are changing the default value of opt_cr. So the syntax is the keyword option, the name of the variable. So in this case we are changing opt_cr is equal to a very small value, right. So when we solve with this statement, we get a solution of 726.06789, and over here previously we had got a statement which said solution satisfies tolerance. Here in the log file we get proven optimal solution, and this absolute gap and relative gap, if we see, previously this was 51.87, now it is 0, the absolute gap is almost 0 and the relative gap is almost 0, right. So the profit now is 726.0068, right, and these are the corresponding decision variables which you can get from the list file. So this shows the change in decision variables and the objective function value for default option. So in this case the opt_cr was not set, so when it is not set, its default value is taken, which is 0.1. So, for the second case, for the same problem, when we changed opt_CR to a very small value, we were able to get a better profit, and the absolute gap and relative gap are now almost close to 0, right. So, previously we got this solution in just 4 iterations, now it requires 1376 iterations, so that this opt_CR condition is satisfied, right. So, as you can see, there can be significant difference. So, for example, let us say the unit of profit was millions of dollar, right. So, here we get a difference of almost $14 million, right. So, this part of the discussion, particularly on options, we have intentionally included so that you understand that it is not sufficient to just solve a problem. We also need to ensure that the algorithm has a termination which is satisfactory to us, right. So, previously we had seen that the absolute gap is very high, right. We should not end our exercise just by determining the objective function value and the decision variable, but we also need to analyze the reason for the termination of the algorithm, right. And if certain settings need to be revised, we need to revise those settings and solve the problem, so that we may get a better solution. So, additional details on this settings of opt_CA, opt_CR with respect to GAMS as well as with respect to solver can be obtained from here. So, now let us execute the code of production planning problem into you. So, we have 3 sets, set J, set LEV and set K, right. So, set J contains 54 values, the values are 1, 2, 3, 4 all the way up to 54. The set LEV contains the value L, M and H, and the set K contains the value R1 and R2, right. So, over here we are defining all the data which has been given to us, and then we have defined these 2 parameters, right. So, these 2 parameters are for the raw material 1 and raw material 2. This is the scalar which defines the budget value. These are our 6 decision variables, right. So, all of them run over the set J. So, set J contains 54 values. So, this is 54 into 6 decision variables, right. In addition to that, the objective function has to be defined as a variable in GAMS. So, that is why we have this additional variable obj, and we have 2 sets of binary variables. So, y and z are binary variables. So, we define binary variables and define what are those variables. Over here we have 7 types of constraint, and then we have the equation for profit, right. So, the names of all the constraints are defined over here. Among these, equation 4, equation 1, equation 2, equation 3, equation 5 run over all the process, right. So, those have to be written 54 times, and equation 7 has to be written 2 times because we have 2 raw materials which are available in limited quantities, right. So, when we showed you the data, we showed you 3 raw materials, but since there is no constraint on the 3rd raw material, there is no point of including it GAMS file, right. Had there been any constraint involving it, we can include it in a manner similar to R1 and R2, right. So, over here as discussed earlier, we have written all the constraints, right. Then we are building the model whose name is petrochemical, and we are including all the constraints written in this file in the petrochemical model, and then over here we are solving using a mixed integer programming solver. We want to maximize the objective function. The objective function corresponds to this variable obj, and we are solving the model petrochemical, right. So, at the end of the solution procedure, we want GAMS to display the final values of the 6 set of decision variables, right. We can either click on F9 or click on this button to run it, right. So, over here is, so this is the list file, right. So, this is the GAMS file which we had written, this is the list file, and this is the log file over here. So, if we say open log file will also be opened in the editor window. So, this is the editor window, right. So, let us look into the list file. This is the indexing for the list file, right. So, if we go to the display part, these are our solutions, right. So, for process 3 we need to produce 310, for process 4 we need to produce 215.59, for 46, 47, 48 the appropriate value. So, all the L variables have taken a value of 0. So, over here if you see, when we display x dot L, it only displays the non-zero values. If you remember what we did in MATLAB, we had to write a small piece of code to ensure that we get only the non-zero values. Over here when we display, it displays only the non-zero values, right. So, only 3 variables of M are active, right, for process 4, process 46 and for process 47, right. For all the other process, L value is also 0, M value is also 0, except for these 4 processes, the H value is 0 for all of the other processes. Similarly, the variable Y value is given over here, and Z value is given for only these 4 processes, 3, 4, 46, 47 and 48. Those are the only process which are having some production quantity, right. So that is the display statement. Let us look at the model statistics. So the model which we solved has 325 single variables. So we have 54 processes. So 54 into 2, right, for y and z. So we get 108 variables, and there are 274 equations. So here if we look at the solution report, right, so the objective function value which we obtain is 712.504, right, and it indicates that the completion is a normal completion. What is being reported is an integer solution, right, and resource usage, if we see, out of 1000 seconds it has used 0.453 seconds to solve this problem, and out of these many iterations, which is the default value in GAMS, it used only 6 iterations, right. So now if we go and include this option over here, right, so we are changing the default option. The default option is opt_cr is equal to 0.1, right. So the solution which we got over here satisfies the tolerance, right. So that is why it terminated, right. So let us close this file. Now we are solving after including this option statement, right. So this one. So if we look at our list statement, if you remember our previous x, this has changed, right, and our objective function value, previously it was 712, now it is 726.007, right. So we get an improved solution. So that is why it is important that once we get a solution, we also look into the reason for termination, right. So in this case, the reason for termination would be solution report, right. So here previously, if you remember, we had solution satisfies tolerance, right. So now it is proven optimal solution. So for Simplex, solution is proven optimal solution. Previously it took very few iterations, now it has taken 1417 iterations to reach this solution, right. And now if we see, the absolute gap and the relative gap is 0, right. So previously without this, if we execute, the absolute gap, if we see, it is 51.877 and the relative tolerance is 0.06, right. Since the relative tolerance satisfies default value, it is terminating. Now if we look at the absolute gap, it is very high, and here also it explicitly says that the solution satisfies tolerance. It is not saying proven optimal solution, right. So that is why it is important to look at the result, right, not only in terms of the values given by GAMS, but also the reason for termination, and if required we need to change the options and then rerun the problem so that we can get a better solution. So now that we have solved the production planning problem with meta-heuristic techniques, as well as we have formulated it as an MILP and solved it with GAMS. Now let us compare the results which we obtained from meta-heuristic techniques and those we obtained from GAMS. So in this slide we have consolidated all the results, right. This section shows the results by meta-heuristic technique, right. So in meta-heuristic technique, if you remember, we had employed 2 approaches, right. So the first one was we were doing without correction. In without correction, our algorithm would only send the decision variables, right, whereas the problem would evaluate the decision variable and would send back the fitness function value, right. So over here we had 3 types of constraints: a domain constraint, budget constraint, and 2 raw material constraints, right. So in this case, what we were doing is we were merely evaluating fitness of the solution given by the algorithm and returning it back to the algorithm, right. So here in without correction, we were penalizing for all these 3 types of constraint, right, whereas in the correction approach, our algorithm would still send only the decision variables, right, whereas our problem statement would send back the corrected decision variables and the fitness function corresponding to it. So here we, in this problem statement itself, we corrected for the domain constraint, right. So domain constraint, if you remember, for the meta-heuristic technique, the bounds are between 0 and h. It can give any value between 0 and h, right, whereas in our problem we had this constraint that a value should be either 0 or it has to be greater than or equal to L and less than or equal to h, right. This was the permissible domain. So in correction approach, what we did is, if the value comes somewhere over here in between L and H, it is fine. If it is 0, it is fine, but if it is greater than 0, we reassign the value of the decision variable to 0. So that is the correction approach which we had employed, right. So when we employed correction approach, we no longer have penalty for domain constraint, because that constraint is being taken care by the correction approach. So we had penalty only for the budget constraint and the 2 raw material constraints, right, and we evaluated the fitness of the corrected solution, right, and the corrected solution also has to be returned back to the algorithm. So that was our correction approach, right. All this we have discussed previously. you can go back and have a look at it. So, for both the approaches, with correction and without correction, we solved the production planning problem with teaching learning based optimization, differential evolution and particle swarm optimization. We had chosen these three techniques because for these three techniques the number of fitness function evaluation is uniquely fixed if we fix the number of iterations and the population size. So, right. So, for TLBO it was NP plus 2 NPT, whereas for DE and particle swarm it was NP plus NPT, right. So, that is why we had taken only these three algorithms. You can do similar comparison including genetic algorithm and artificial bee colony optimization. So, here we have 4 cases. So, this is case 1, case 2, case 3 and case 4. How do these cases differ is based on the amount of budget and the raw material 1 and 2 which are available. If we say that this is case A, right. So, in case A the amount of budget that is available is 1000. So, the amount of raw material 1 and 2 that is available is 500. In case B the amount of budget that is available is still 1000, whereas the amount of R1 and R2 which are available are 1000. For case C and case D the total amount of budget available is 2000, and for case C the amount of raw material available is 500, and for case D the amount of raw material available is 1000. So, these are the results which we had obtained using GAMS, right. So, GAMS also, if you recollect, depending upon this opt-CR setting, we did get different results, right. So, first we executed all these 4 cases with the default opt-CR, right. So, we did not specify opt-CR itself. The relative gap was at its default value, right. So, in those 4 cases this is the profit that we obtained, and these are the 4 cases wherein we had set opt-CR to be this value. Among these 4 cases, if we see, in 2 cases we get a better result. So, here we get a better result and here we get a better result. So, here it is 113.15, here we have 1173.11, here it is 712.50, here it is 726.01, right. So, we have given you the GAMS code. We expect you to go back and execute the program with this opt-CR and again check whether with this opt-CR do we really get the proven optimal solution, or is it terminating for some other reason, right. So, if it is terminating for some other reason, then we need to appropriately change the option corresponding to it to see if we get a better solution. So, these are the solutions obtained for the 4 cases by the 3 different algorithms, right. So, DE was not able to determine even a feasible solution. So, here if we compare within the meta heuristic techniques, in this case we got PSO performing better, whereas here we got again PSO to be better, and in these 2 cases TLBO was better, right. So, DE was consistently inferior for the algorithm settings which we had taken. With different parameter settings we might get a different value, and these are the results with respect to correction approach, right. So, in this case we had also previously seen that correction approach gives a better solution than without correction, right. So, in this case if we look for case A, so the best solution that we obtain for meta heuristic techniques is 710.04, right, whereas that what we obtain from the MILP formulation. So, when we say here GAMS, it is the MILP formulation which we have discussed solved with GAMS. So, here we get a value of 726.01, right. For the second case, if we see, the best value that we get from any meta heuristic technique is with DE, right. So, here we have 816.72, whereas what we get from the MILP formulation is 834.30. Similarly, for the third case, if we see, the best value that we have is 1092.3, whereas the best value that we get from the MILP formulation is 1173.11, and for the fourth case also the best value that we have is 1375.50, and over here it is 1452.82. Right. So, in all the 4 cases the solution that we get from the MILP formulation in GAMS with the appropriate settings is better than what we got in the meta heuristic technique, right. This result comparison should help you to understand that it is worth the effort for transforming the problem statement into a mathematical formulation, right. So, if the mathematical formulation happens to be a linear programming or mixed integer linear programming, there is a reasonable chance that we will be able to get the global optimal solution. Another thing you need to remember is that when we use meta heuristic techniques, right, we have to execute multiple runs, right. So, what we have shown you is the result of the best run, and again there are issues with setting the tuning parameters, right. Whereas in the MILP formulation, we did not have to execute it multiple times, it is a deterministic algorithm. So, similar to the settings we have to do for meta heuristic techniques, for solving the MILP formulation also we need to set a large number of factors. So, the results that we get is dependent to a large extent on the settings that we employ for solving the mixed integer linear programming problem. So, now that we have seen GAMS, right, so let us look into Neos server. Neos server is particularly useful when we do not have a license, right. The demo license which we use is only for a restricted number of variables and constraints, right. Now, let us look into how to solve a problem using the Neos server. So, this is the website for Neos, right. So, neos-server.org/Neos. So, if you look into here, you will get lot of information about Neos server, including some case studies. The case studies have been divided into certain areas like bioengineering, computer science, economics and game theory, image processing, optimal power flow, optimization methodology, puzzles and supply chain, right. If we look into puzzles, so there are these 5 puzzles which can be solved using a GAMS code, right. So, if we click in on the Sudoku problem, this is the mixed integer linear programming problem for Sudoku problem, right. So, here they have given AMPL model. So, this Neos server supports not only GAMS model, but it supports various other types of models, right. So, if you want to submit a job to Neos, we need to click over here, submit a job to Neos, and then over here we need to look for the appropriate solver that we want to solve, right. So, for example, under global optimization we have these many solvers. So, not every solver is compatible to get every type of inputs. Over here this ASA accepts only AMPL input, whereas the solver Baron accepts AMPL input as well as GAMS input, right. So, let us click on GAMS input because we have a GAMS file now. We are going to solve a nonlinear programming problem, right. So, the problem that we have is downloaded from gamsworld.org. This gamsworld.org has a collection of test problems, right. So, as you can see, this particular problem has a large number of variables, right. It has 2583 constraints and it has 2282 variables. If we run this file over here, right, so since we have only a demo license, right, it gives a message status terminated due to a licensing error. If you happen to face this type of licensing error, so then we can choose the Neos solver, right. So, but if there is some error in this file, so for example, let us just introduce an error over here. Let us just remove this comma, right. So, now if we run it over here, it will not give a termination error, but it will give a compilation error, right. So, there is an error, right. So, that way even though we have only a demo license, we can ensure that our code is running fine. So, once we know that the code is working fine, we can upload it onto the Neos server for solving purpose, right. So, let us go back and put this comma again, right. So, now if we execute this file as previously, we should get a licensing error, right. So, terminated due to a licensing error, right. So, let us now go back to this Baron solver, right. So, we need to first submit our model file. So, choose file. So, this is the model file that we want to solve. So, we upload that file, right. So, if we have an options file, we can give that option file. This GDX file we have not discussed, right, but it can be used to give inputs to the GAMS code, right. So, if we require a log file, we need to click this checkbox, and over here we can give some comments, right. So, over here we can give a email ID. So, the results would be sent to this email ID also. We can see the results over here as well as we can get the results over email, right. So, we need to give submit to Neos. So, depending upon the queue on the server, right, our problem will be placed in a waiting list. Usually it does not take much time to clear the queue, right. So, over here we have been assigned a job number. So, this is our job number 7984917 and a password is shown over here, right. So, now the job is completed, it was awaiting for results. Now, we have been able to get our results, right. So, the job number, password, right, and after this whatever we had discussed in the list file holds true over here. This is the list file. So, our solver status is normal completion. So, the objective function value is 3795.2061, right. So, we had 2583 equations and 2283 variables. The results are also emailed to us, right. In this case we had given our email ID, right. So, this is our job number. So, we have received this email from Neos, right. So, since the job results were too long for email, the results may be downloaded from this link. They have provided the job number and the password. So, if we click on this, so this is the job number that we gave and this is the password. right. So, we want to view the job results. Right. So, this is the same file which we see over here, right, which we had got after solving it, right. So, if it takes a little bit longer to solve depending upon the queue, we can also get the results through the details given in the email, right. So, in this case the problem was a bigger problem. So, we did not get the list file as part of the email, otherwise we would also get the result file as part of the email itself. So, if you remember, we had also requested for the log file. If you click on that, then this will contain our log file. So, this is our log file. Here we can see the actual absolute gap and the relative gap and the default options. In this case, we did not change the default option. So, the default option for opt-CA is 10 power minus 9 and the default option for opt-CR is 0.1. Similar to our discussion with Simplex, Baron also uses a different formula to compute the relative gap. Additional details on this you can find from the solver manual of Baron. So, in this offline help documentation, so we have the solver manuals also. So, each solver has its own manual. So, one can go into this Baron manual and look into further details about calculation of opt-CR and other relevant things. This is how we can use GAMS and Neo server to solve problems involving larger number of decision variables and constraints. So, while installing GAMS, you would have seen two options. One is GAMS IDE, another one is GAMS Studio, right. So, if you look into GAMS Studio, from here we can get lot of details, right. So, for example, the transportation example which we have discussed previously is directly accessible from here. It also gives an introduction video about GAMS Studio, right. So, it links to YouTube. It also provides a lot of other information. We leave it to you to explore that. You can also visit this GAMS World Forum to interact with the user community, right. So, here you will see something called as Miro, and by default it would be disabled if you are working with a demo license. So, you can have a look at it over here, gams.com/Nero. For GAMS Miro, you need to have an additional license, right. So, over here a large number of examples are already given. Let us look at couple of examples which they already have. So, one is the transportation problem. It gives details of the problem. To remember the problem, we had two plants whose capacity is to be specified, right. So, over here we can change the inputs, right, 400 and 700, let us say. And then each of the three markets, New York, Chicago, Topeka, had its own demand, and we also had specified the distance between the market and the plants, right. So, the plants were located at Seattle and San Diego, and the markets were New York, Chicago and Topeka. So, the model has already been deployed using Miro. That is why we are able to see this, right. So, here if we solve this model, so we have this listing file. We have discussed the contents of the listing file and log file earlier. So, over here if we see, they have given the procedure how to develop, how to use our GAMS model with Miro. So, here they have shown it for the transportation problem, right. So, this is the transportation problem which we had discussed. We need to add a few statements to our model so that it can be executed on Miros. We can have our model deployed over the web. So, the another example which they have is the Sudoku example. If you look at input, this is the input, right. In this case, they have something called as force unique solution. So, if this is on, it will compute a solution only if the solution is unique. Let us put it off, right, and over here let us say we give a value of 4, 8, 7, 6 over here, and if we solve the model, so it displays the solved Sudoku problem, right. So, the values which we gave were 6 over here, 4 over here, 7 over here and 8 over here. So, it has been able to find out the rest of the entries while satisfying all these constraints, right. So, here we have not looked into the formulation which is actually solving this problem. Similar to the transportation example, a GAMS file can be developed for the mixed integer linear programming model, right, and that can be deployed using the Nero software. So, as it can be seen that GAMS along with Neo's server can be used to solve problems involving large number of variables and constraints, and we can also easily deploy our model using the Miro software. In this session, we have seen how to use GAMS to solve linear programming problems, non-linear programming problems, mixed integer linear programming problems and mixed integer non-linear programming problems. Additionally, we also saw how to code the production planning problem in GAMS and how to analyze the results. With that, we will conclude this session. Thank you.